This is video lecture number 2 for chapter 24, so if you can turn to the appropriate page. A nuclear reaction is one in which the nuclei of an unstable isotope, which we call a radioisotope, gain stability by undergoing changes in the nucleus itself. So nuclear chemistry changes in the nucleus. Unlike the chemical reaction, nuclear reactions are not affected by temperature, pressure, or even the presence of a catalyst. Radioactive decay is spontaneous, which means it occurs without outside intervention. All elements above bismuth, which is atomic number 83, are radioactive. But there are many isotopes less than atomic number 83 that are also radioactive. In fact, of about 1,500 different isotopes that we know of, only 264 are stable and do not decay with time. The stability of an isotope depends on the ratio of neutrons to protons in the nucleus. For the lighter elements, the neutron to proton ratio is 1 to 1. So if we look at carbon 12 has 6 protons, and subtract the two numbers, it has 6 neutrons, which is a 1 to 1 ratio. For the heavier elements, the ratio of neutron to protons is about 1.5 to 1. So as you get more protons, you need even more neutrons to keep the nucleus from blowing apart. So if we look at 10 neutrons versus 10 protons, a 1 to 1 ratio, we see we have stable isotopes here. So all of the dots represent stable isotopes. But as you get to atomic number 60, we see that a 1 to 1 ratio is not within the area of where the stable isotopes are. You have many more neutrons compared to protons to keep the nucleus from decaying. When a nucleus decays, it decays according to a half-life. A half-life is the time required for half of a nuclei to decay into products. After one half-life, half of the original radioactive material has decayed into a new element. So radium-226, we would look up atomic number 88, has a half-life of 1,600 years. It transmutes into radon-222. So then we could figure out it is by alpha decay. And if we were to make a chart, we would see if we started with 16 grams, originally there would be 16 grams of radium-226, no radon-222. We would have gone through no half-lives, so 100% remains. If we come back 1,600 years later, half of the radium-226 would decay, so there would be 8 grams left, and we would have 8 grams of radon-222 forming. And it went through one half-life. So each half-life, you lose half of what's left. So 16 to 8 is one half-life. Then it would go down to 4 for the second half-life, to 2 for the third half-life, down to 1, and then 0.5. So if we were to graph this data, we would end up with this downward sloping curve. And this is the graph of a half-life. We have an equation for calculating half-life, but we're not really going to use it in this class. Instead, I will show you a simpler way. And then finally for today, we have table N, which we looked at. We can determine the type of decay that a isotope goes under. And then we can use table O to determine or to write the equation for the decay of that isotope. And we can even see the half-life it takes to decay into the stable isotope. So cobalt-60, and we look up cobalt, and we see it is atomic number 27. It will decay by beta decay into atomic number 28, nickel, and it will decay into nickel according to its half-life. So every 5.271 years, half of the sample of cobalt-60 will turn into nickel-60. And that is it for today, and we will see you in class.